Alright, so let's discuss what happens when we have complex eigenvalues and eigenvectors. So we know eigenvalues come in conjugate pairs, and so do their corresponding eigenvectors. So suppose we have an eigenvalue corresponding to an eigenvector b, then we also have the conjugate of this eigenvalue corresponding to the conjugate of this eigenvector. So the solution corresponding to this pair of eigenvalue eigenvectors is C1 times e to the lambda t times v plus C2 times e to the lambda bar t times v bar. Now, if we simplify everything, so this, after all the algebra, this is a complex vector, so it has the real part and the imaginary part, w times I. Then the conjugate of that is gonna be u minus w times I, still real part, and the imaginary part. So this is equal to C1 times u plus wi plus C2 times u minus wi. So this is equal to C1 plus C2 times u plus C1 minus C2 times I times w. So in other words, the original solution is a linear combination of these two complex value functions, but it can also be expressed as a linear combination of u and w, which are real functions. So these are real functions, or vectors, vector functions. So we can choose x1 to be u and x2 to be w for convenience, because these have no complex numbers in it. And u and w is the real part of e to the lambda t v, and w is the imaginary part of e to the lambda p t times v. Alright, so let's do an example to verify this. So let's do an example. Suppose x prime is equal to x prime. The vector x prime is equal to the matrix 4, negative 3, 3, 4 times x. Then first we do is we try to diagonalize this matrix. So we solve the characteristic equation, which is determinant of a minus lambda I equal to 0. So 4 minus lambda, negative 3, 3, 4 minus lambda equal to 0. So 4 minus lambda squared minus negative 3 times 3 equal to 0. 4 minus lambda squared, or lambda minus 4 squared is equal to negative 9. So lambda minus 4 is the plus minus the square root of negative 9, which is plus minus 3i. So lambda is 4 plus minus 3i. So because they come in pairs, so all we need to solve is the eigenvector corresponding to one of them. So let's consider lambda is 4 plus 3i. Then we want to solve 4 minus 4 plus 3i, negative 3, 3, 4 minus 4 plus 3i times v equal to 0. So this is negative 3i, negative 3, 3, negative 3i, v equal to 0. So solution to this, so you can solve this directly. So we get negative 3i times v1 minus 3v2 equal to 0. So v2 is negative v1 times I. So a solution will be v equal to 1 negative I. That's the solution. Alright, so that's our eigenvalue with corresponding eigenvector. So now we calculate this function e to the lambda t times v. vector function. So this is equal to e to the 4 plus 3i times the vector 1 negative I. So this is e to the 4, I forgot a t here, e to the 4t times e to the 3it times 1 negative I, e to the 4t. Recall the Euler's formula, e to the 3it is cosine 3t plus I sine 3t. And multiply this by 1 negative I. Let's move a little bit. So this is e to the 4t. Multiply, this is a constant, so I multiply by into each component. So the first component is 1, so just cosine 3t plus I sine 3t. The second component is negative I, so we get negative I cosine 3t minus I squared, that means plus 1, plus I plus sine 3t. And now let's separate the real and the imaginary part. So the real part is cosine 3t sine 3t, and the imaginary part is sine 3t negative cosine 3t. So this is equal to e to the 4t times cosine 3t sine 3t plus I times e to the 4t times sine 3t negative cosine 3t. So this is our u, which is the real part, and this is our w, which is the imaginary part. So we can choose our x1 to be u and x2 to be w. So the general solution is x of t equal to c1 times x1, which is e to the 4t times cosine 3t sine 3t plus c2 times w, which is e to the 4t times sine 3t negative cosine 3t. And if we want to write it in the scalar form, then this means x1 is equal to c1 e to the 4t times cosine 3t plus c2 times e to the 4t times sine 3t. And x2 is c1 times e to the 4t times sine 3t minus c2 times e to the 4t times cosine 3t. All right.